We're starting our last unit in AP Chemistry, and that is electrochemistry. This is lesson 1, our introduction. We've got a few preliminary ideas that we need to get across before we get into the real thing. First of all, it is recognizing that all the reactions that we're going to be looking at in electro involve the transfer of electrons. Those are called redox reactions because we have something that is oxidized and something that's reduced. So redox. All right. Our job is first of all to distinguish if a reaction involves the transfer of electrons, and we'll get to that a little later. And then if it does, then what particular species in the reaction was oxidized and which was reduced. This is a transfer of reactions, transfer of electrons. I have got that in your notes as a reaction that involves the transfer of electrons. One species is reduced and the other is oxidized. All right, classic example. Classic example is single replacement. You've seen these a lot on your Friday reaction predictions. And what I have in this little beaker is a solution of silver nitrate. All right, it is silver nitrate dissolved in water. Okay, so in this aqueous solution are silver ions and nitrate ions. All right, this is a colorless solution because to have color we have to have partially filled d orbitals, and we know the off-bow exception that silver has it's got its d orbitals completely filled. This is elemental copper. All right, and when I put this copper into this silver nitrate, we're going to see something that happens. Now this will take a while, so I'll set it down and we'll refer back to it. But as you can see, maybe closer inspection, that the copper is turning kind of silverish. And what we're having, this is single replacement, that the silver ions are actually getting an electron from the copper and plating out into elemental silver on the wire. And then what's happening is the copper is losing its electrons and it's being transferred to a copper 2+. So what we'll actually see as this reaction progresses, obviously it's rather slow, isn't it, coming out of kinetics, not a real fast reaction, is that the solution will go from colorless to a pale blue because we know that copper 2 ion does have partially filled d orbitals and will have color. So I'm going to set this aside and we'll refer to it a little later. But let's look at this reaction. We have copper metal is placed in an aqueous solution of silver nitrate. We don't need parentheses, silver is +1. Sorry about that. All right, and then what's going to happen is that we have single replacement. The metals are going to switch places, we've said. And then the silver will come out and the copper will go into solution. All right. We kind of did this experiment earlier in the year with the nail in the copper 2 nitrate and the iron and the copper switch places, and we scraped that off. Remember, when we looked at it from a stoichiometry perspective, we might actually do that again now and look at it from a electron and electro perspective. But anyways, the idea now is to see how the electrons were transferred. So to do that, we pull out the half reactions, what they're called. We look at the two things that actually changed in their charge or were affected by these electrons. The nitrate, spectator, nothing happened. All right, and right now you can see this is not balanced. All right, we'll worry about that in just a minute. So let's look at our first half reaction and say, well, what happened to the copper? In this reaction, copper went from a neutral element into a +2 ion, all right? And what happened to the silver? Well, the silver was an ion to start with and went to the elemental state. All right, and once again, you know, maybe you don't see that. Let's just look at what happened to nitrate. Nitrate went from -1 to -1. All right, so nothing happened as far as electron transfers to the nitrate. Okay, so this is why, first of all, it says solution, our balanced chemical equation wouldn't have that, you know, our net ionic wouldn't have that, but this is why nothing happens to the nitrate. Okay, so we've identified and shown in a half reaction what happened to the copper, in a half reaction what happened to the silver, and now it's analyzing it further. Which one was reduced and which one was oxidized? Well, if it's oxidized, it lost electrons. How do we know if it lost electrons? Well, the charge becomes more positive, doesn't it? If I lose electrons, then I'm going to, that ratio of protons to electrons will tip in favor of protons. And I can say exactly how many electrons did I lose is because this is where not only an equation do we need to balance mass. In other words, if I start with 1 copper, I end with 1 copper. But we need to balance charge as well. If I'm at 0 on this side and a +2 on this side, I'm not equal. The only way that we can balance charge is by adding electrons. All right? So I look and I say, by adding electrons, how does this work? Well, all right. So now we've written this showing the loss of electrons. Okay, how do we know they were lost? First of all, because of this charge, and second of all, because the electrons are placed on the product side. Okay, in going from copper to copper 2+, 2 electrons were lost. Kind of like thermo. If the energy's on the product side, it's released, isn't it? It's lost. Okay, now we're going to do the same thing with this. All right, so we're going to say that the copper was oxidized. Now we're going to look at what happened to the silver. The silver went from plus to 0. Okay, it became less positive. All right, if it became less positive, it did so by gaining an electron. Right, this is the whole thing is a transfer of electrons. So how many electrons? Well, we got to balance that charge, don't we? So we put 1 electron over here on the reactant side. Right, so now we have a charge of 0 on the reactant side and a charge of 0 on the product side. So our charge and mass balance, and that is what we have to have. All right, we see that silver picked up this electron. So silver was reduced. Okay, so first of all, we have identified this as a redox reaction, because we can validate that an electron was transferred. We've also, by writing half reaction, have shown which species was oxidized and which species was reduced. All right, so those 2 things. Now, if we put these together, we can also use half reactions to balance this equation. Remember I said up here this wasn't exactly balanced, was it? All right, well now we'll see why it's balanced, because it all gets down to charge. All right, we're kind of going full circle here with chemistry. If I lost 2 electrons, I better have gained 2 electrons. So what do I do to have 2 here? Well, I multiply everything times 2. So 2, 2, and 2. Now my electrons cancel, and if I write the balanced net ionic equation, all right, and so that is the balanced net ionic equation. And this is showing it from how the electrons were transferred. All right. Let's look back at our little reaction here. See how that solution is turning blue? That is what we have written on the board. Okay? as the silver is replacing, see how it's getting fuzzy, that silver on the wire? It is replacing the copper. The copper is going from elemental neutral state to a +2. As it goes to a +2, then we have that blue colored solution because of those partially filled d orbitals. So we can see there's several evidences that something is going on, all right? If we were to mass the copper, we would see it lost mass. If we were to say, well, there's another metal that appears to be plating out, all right, and our solution went from colorless to a pale blue. So there's several evidences. If we were monitoring the temperature, we could probably even see if this was exothermic or endothermic, this process. I'm going to show the other single replacement, just because this is the one that you guys usually mess up on reaction predictions. Okay? Because that was metal single replacement, but we can also have halogen single replacement, correct? And what you guys usually mess up is the diatomics, okay? So, chlorine gas is bubbled through a solution of sodium iodide. All right, okay, well this is double replacement of a halogen. Single replacement of a halogen. However, as an ion, it has to match charge of the compound it's with, but when it's by itself, it's diatomic. So when we have this, the single replacement looks like that. Okay, then obviously we'd have to balance it, but let's just see this for a minute. Okay, now if I were to say, is this a redox reaction? Well, we'd have to say, was there a transfer of electrons? So let's look at each species. All right, the half reaction for chlorine. Chlorine went from elemental state, that was neutral, to a -1. All right? Okay, now let's look at what happened to the iodine. The iodine went from a -1 to a neutral element. We also have sodium in there, and let's just see what happens to sodium. It went from +1 to +1. So obviously nothing happened from a redox perspective to the sodium, spectator ion in a sense. So we can ignore the sodium. All right, now it's looking and saying, well, what is oxidized and what is reduced? All right, and this time we might balance the mass first because we've got 2 chlorines here, don't we? So we better have 2 chlorines over there. All right, so first of all, we've balanced mass. And now we need to balance charge. All right, well, this went from a 0 to a -2. The only way that we can balance charge is by adding electrons on one side or the other. Well, this picked up 2 electrons, and so now I've got a -2 on this side and a -2 on that side. All right, it's just the charge has to balance. It doesn't have to be, we have to have both sides 0. Okay, now let's do the same thing for this. We need to balance the mass first. I balanced the mass by 2 iodines, 2 iodines. Okay. This side has a -2, this side has a 0, so I can add 2 electrons over here and make this one balance. All right, now it's which is oxidized and which is reduced. All right, well the chlorine is reduced because it gained 2 electrons. All right, reduction is gain, which really makes sense. So the chlorine is reduced. The iodine lost 2 electrons. So iodine is oxidized. I guess you would say it from the perspective of whatever is the reactant. All right. Okay, now how do you remember that whatever gains is reduced and whatever loses is oxidized? Well, there's two acronyms. One is Leo says grr. Okay, Leo the lion growls. All right, loss of electrons is oxidation. Gain of electrons is reduction. And, you know, if you're not into Leo the lion, there's also this, oil rig. All right, oxidation is lost, reduction is gained. So that helps you to keep which is which of these processes. Okay, and once again, in how this chlorine gas is bubbled through a solution of sodium iodide. Okay, so we would have a colorless solution, right? And chlorine gas is a yellow gas. All right, so as we bubble this through the chlorine gas, this yellow gas is going to disappear, isn't it, into a chloride ion. All right, so we would have a yellow gas that goes into colorless solution. And then we would have a colorless iodide, right, that goes into a purple solid, wouldn't we? All right, and it might be more brownish, you know, pure iodine is purple, but in reacting with that yellow, it can take on a brownish tint. But this would be the evidence that something was going on. All right, sometimes thinking of evidence, we can make it harder than it actually is. All right, so with ionic compounds and elements, this is pretty straightforward. We look at the charge of the ion in the compound. We know the element is 0, and it's really easy to follow where the electrons went. All right. But what if this is a molecular equation? What if we have something like this? Methane is fully combusted. And we'll go ahead and balance it just for the heck of it. Okay. All right, and I said, is this a redox reaction? Well, we don't have charges from ionic compounds to follow those electrons. Okay, so when we're in a situation like this, we've come up with a system of assigning charges, all right? Because they're not really charges, we call it assigning oxidation states. And if you remember, way back in August when the school year started, reaction prediction number 2 was giving you practice on assigning oxidation states. But since I know you probably have no recollection of what went on in August, let's review this for a moment. Okay, so the idea is, first of all, is this a redox reaction? All right, the others were easy because we just had ionic compounds, they had charge, and we looked at what happened to the charge of an ionic compound. No problem. What if we don't have a charge to work with? We don't have an ionic compound, we have molecular. By definition, molecular do not form ions, correct? They're sharing their electrons, and they remain neutral overall. So how would I do this? Well, we've come up with a way of assigning a charge to the atoms in a molecular compound. And just for review, I've put those little rules over here on the right side of page 1 of your lecture notes. And so what we would do is these are written in order of importance. First of all, it's remembering if you have an element such as this, recognize an element, by definition it's neutral, it has no charge. Okay? It's not an element if it's got a charge. It's 9 on them. Okay? If we do have ions, we don't have to pretend. Okay? It's the real thing. So if you have an ionic compound or polyatomic ion, the charge is the oxidation state. Okay? When we have a compound, if I add up the oxidation states of the atoms, it must be equal to 0. If it's a polyatomic ion, and I add up the oxidation states, it must equal that -1. So the total number must reflect if it's a neutral compound or the charge of a polyatomic ion. Now, how do we assign? We always look and say, in our compounds, which one is on this list? First of all, fluorine is always a -1. So, you know, if you had this compound, you would say, fluorine's got a -1. Okay? Second is that hydrogen is usually a +1. The only time it would not be a +1 is if it's in a funky arrangement with fluorine or in an ionic compound and it's acting as a hydride, you know, like calcium hydride, it would have a -1. But we're generally going to assume that it's got a +1. All right, and then third is oxygen usually has a -2. All right, unless it's in a funky arrangement with hydrogen or fluorine, like in hydrogen peroxide, then it doesn't have. Okay, you go with what's on the top of the list here. We've got hydrogen above oxygen. Okay, all others can vary. So what you're going to do is, when you're given a compound, you're always going to start with element that we know something about. All right, for instance, in this compound, hydrogen is on the list. Carbon is one of those that can vary. So I'm going to start with hydrogen. All right, and I use what I call this little box method. I start and say, what does 1 have a charge of? Well, 1 hydrogen has a charge of +1 from my rules. Okay, on the bottom is the total because of the subscript, all right? So there's 4 hydrogens, they each have 1, so they're going to have a total of 4. According to the rules, this compound must be neutral. So on this side, it's going to have an overall -4. All right? Since there's only 1, each one will have a -4. Okay? So, in looking at my half reactions, and half reactions don't work so well with molecular, but we'll just say, so instead of calling it half, let's just say what happens to everybody. Here's carbon. Carbon is going from a -4 to something else. All right? We know this is an element, so it has an oxidation state of 0. Okay? Now we move over to the products. I'm going to start with oxygen because that's on my list of rules. And it says oxygen is usually a -2. So my little box set up again. 1 oxygen has a -2. Because there's 2, it's going to have an overall -4. Okay, we said from our rules that this must be neutral. So my overall positive must be +4. Because there's only 1 carbon, that 1 carbon will have a +4. Okay, so that means my carbon goes from a -4 to a +4. All right. Now, what happened to the oxygen? The oxygen went from 0, didn't it, to a -2. And then we're going to see that the hydrogen remained unchanged, didn't it? Okay, so the hydrogen remained unchanged. So what numerically happened to carbon? All right? It became more positive. It lost electrons. Okay? In fact, we could even say lost 8 electrons, so to speak, going from a -4 to a +4. So the carbon was oxidized. Well, there's a surprise, it reacted with oxygen. Of course, oxygen's going to take the electrons. Okay, that's what oxygen does. So carbon is oxidized. Oxygen went from a 0 to a -2. It became more negative. It became more negative by a factor of 2, didn't it? All right? So we could say oxygen was reduced. So back to our 2 questions. Is the combustion of methane a redox reaction? Yes, it's a redox reaction because there was a definite transfer in electrons. Okay, the transfer of electrons. Which species is oxidized, which species is reduced? Well, carbon is oxidized and oxygen is reduced. Okay? Great. If you need any more practice with that, go back to your reaction prediction 2, where we discussed that. And I think I even had a tutorial video on assigning oxidation states. All right, page 2 of lesson 1. We can also use doing half reactions to balance chemical equations. Now, a lot of times the ones that we can balance, we can probably balance by observation, and that's always your first go-to in balancing an equation. But if for some reason it's not working, and you've done that other MeNo, start with metals, the ions, non-metals, save oxygen, hydrogen for last, and that's not working, this is another method. Because now you're going to be balancing the equation from the perspective of how the charge changed. Okay? And let's look at one. Here's our unbalanced equation, magnesium and iron, probably iron 3 solution. And what's going to happen is this goes to iron and magnesium 2+. All right? So this is single replacement. Net ionic. I took the chlorate out of that because the chlorate is a spectator. It is a solution. It is soluble. So when we have the unbalanced net ionic equation, all right, and let's say for some reason you couldn't figure this out. So you look at the half reactions and you say, well, iron went from a +3 to neutral, its elemental state. Magnesium went from neutral to a +2. All right? Well, I have one iron. My mass is charged. I've got a +3 and a 0. Well, I better add 3 electrons. Now my charge is balanced. Since it gained electrons, this was reduced, wasn't it? Okay, magnesium went from a 0 to a +2. If I add 2 electrons over here, then my mass and charge balance. 2 plus, 2 minus of 0, this is 0. All right, since this half reaction lost electrons, it was oxidized. All right, the problem is if I add my half reactions up to get the balanced chemical equation for this, I must gain and lose the same number of electrons. Right now I've gained 3 electrons and lost 2 electrons. So what I have to do is make sure that I lose and gain the same number. And I can do that by taking this one times 2 and this one times 3. Because then I'll have 6 electrons and 6 electrons, and they'll cancel out, won't they? What's left is 2Fe3 plus 3Mg goes to 3Mg2 plus 2Fe. Okay, my mass balances 2 irons, 3 magnesiums, 3 magnesiums. Does my charge balance? Well, 2 times 3 is a +6 on this side. 3 times 2 is a +6 on that side. So my charge balances. So there is an alternative way of balancing the net ionic equation for a reaction. This works better with ionic compounds than it does molecular. All right, let's look at our little single replacement one more time. See how fuzzy our metal's getting and see how blue our solution? Those evidences that something did in fact go on. And what's going on will later be what we decide to do with electrochemistry. It's capturing those transferred electrons and doing something useful with them, like creating a battery. All right, so into lesson.